So thanks for the introduction. This is joint work with my advisor, Alexandra Carpentier. The problem I'm going to talk about today is that of non-convex optimization, and in very broad terms, our goal is to find the maximum of a function which is unknown. And we want to do that using as few noisy function evaluations as possible. More precisely, the question I'm going to try to answer today is, can we design adaptive optimization algorithms for this problem? And by adaptive, I mean we should be able to design algorithms that do not require as a hyperparameter something that depends on intrinsic properties of the function f because it is unknown. So the game we play is very simple. The learner is given a budget n of function evaluations and access to an arm space which is simply 0, 1 to the d in my problem. And at each round it may pick some arm in the domain xt, and it receives a noisy reward yt, which is bounded, such that the expectation of yt conditionally on picking always the same location is given by some unknown reward function f of xt. Okay, and I'm going to denote m of f, the maximum value that this function takes over my domain. If we're in the optimization setting, at the end of the game, the learner also has to output a recommendation xn, which it believes to be a good point in the space. So this is quite similar to the best arm identification problem we saw earlier. And we're going to consider two performance measures in this talk. So first, the simple regret, which is simply the regret in optimization that compares how good my recommendation is with respect to the true maximum of the function. And the cumulative regret, which quantifies how good the trajectory of points is with respect to the optimal strategy of always picking the best point for the function. Okay, so my reward function in very broad terms is simply a function from 0, 1 to the d to 0, 1. And if I make no further assumptions, there are lower bounds that tell me that this is an intractable problem. So we're going to make some non-parametric assumptions on f. So first, a regularity condition that's going to characterize the smoothness of my function. And it's characterized by some exponent alpha, which comes up in this expression here. And maybe it looks a little barbaric, but for alpha smaller than 1, just think of my function as being Hölder continuous with exponent alpha, so smoothness alpha. Okay? We're going to couple this with the margin condition, which tells me that there exists some beta such that the volume of the delta optimal regions of the space is bounded as delta to the beta. So for beta equals 0, this imposes no restriction on the function, but generally the larger beta is, the easier the problem is. And the intuition behind that is that if beta is large, there are few zones that are close to the optimum, and a good active strategy should be able to discard all the non-optimal regions rather quickly and focus a lot of its samples on the optimal regions. Okay, so I'm going to call this class of function p of alpha beta, and let me first show you the lower bounds for this problem. So this holds even in the case where alpha and beta are both known and given to the learner. And it tells me that this is the optimal rates we can achieve for the simple regret and the cumulative regret. So notice first that the rate in the cumulative, for the cumulative objective is just n times the rate in the simple regret in this setting. Okay, and this justifies in some sense the setting we just posed because it shows that the more smooth my function is, the better the rate I can achieve. And this beta parameter also interpolates between easy and hard problems with the very interesting case, I believe, of alpha beta equal to d, where this simplifies and the alpha simplifies as well, and we recover the rate of square root n for the cumulative regret. Okay, and our goal today is going to be to try and design procedures that do not have access to alpha and beta and still match those bounds, so in an adaptive fashion. So let me first briefly mention the case where alpha is known. So it's, if you know alpha, what happens is that you can basically use it to estimate the bias of your estimator, and you can construct local upper confidence bands on your function, and you may then choose your next sampling location xt in an optimistic fashion. So this is a rather straightforward adaptation of the UCB kind of strategies to this setting, and we can show that this matches the bound that I just gave. So what happens is that if you know alpha, you may match the bound for both the cumulative regret and the simple regret. And you adapt to beta, the parameter that characterizes the hardness of the problem, naturally. So the question becomes, can we also adapt to alpha for the simple regret and the cumulative regret? So this is very linked to the topic of adaptivity in statistics. And let me make a connection with the canonical problem of estimating a function in subnorm, which is alpha Hölder. Okay. And it's well known that there are adaptive procedures in this setting. So you may use cross-validation or Levsky's method, for example, and you can find a good estimator f hat that does not require as a tuning parameter the true value of alpha, but whose error still scales as alpha. So if you're very smooth, your error is going to be small. And the takeaway is that estimation problems in this setting allow for adaptivity, and this is going to come up for the simple regret, because at heart the simple regret problem is truly an estimation problem. It's something about an intrinsic property of the function, but it doesn't really matter how I know this information at the end of the game. Okay? But the perhaps more surprising result in this line of work is that actually there exists no procedure that also returns some estimate C hat of this C here that has optimal size, meaning that would adapt to alpha as well. Okay? And importantly, there exists no adaptive confidence bounds in L infinity in this setting. Why do I mention that? Well, because if they did exist, it would naturally yield an algorithmic strategy for our problems, because we could plug these adaptive confidence bounds, play optimistically, and recover the adaptive rate. But it doesn't exist. So we either need to develop totally different tools or show that it's also impossible to get adaptive cumulative regret in our setting. Okay, so let me first show you how we get the adaptivity for the optimization setting. The strategy is rather straightforward. So what we do is that we divide our budget in chunks, but they're just of size n divided by log square n, so we don't lose too much because of the log n. We run the non-adaptive procedure that takes alpha as a parameter of our grid of parameters alpha I. And at the end of the game, we get a recommendation from each of these subroutines. We somehow aggregate them, so for example, using a cross-validation scheme, and we recover the optimal rate, but in an adaptive fashion. Okay, rather easy, and this looks very much like an estimation problem. That's why we get the adaptive rate. But the problem we have with this strategy is that it doesn't translate at all to the cumulative regret problem. What happens is that this previous strategy trades off a lot of exploitation in favor of exploration. And more precisely, we can show rather quickly that this has linear regret, because whenever I run my strategy that requires alpha as a parameter with an alpha that's too small or way too large, I cannot say anything about the cumulative regret that I accumulate, and so it doesn't work. Okay? So the question becomes, can we adaptively balance exploration and exploitation in this setting? And our main result is to show that it's actually impossible to do so. So let me walk you through this result. So fix two smoothness parameters, gamma and alpha. What we show is that if you want to pay a certain rate over the smaller class indexed by gamma, then there exists a problem in the larger class indexed by alpha on which you have to pay, in expectation, this regret, which grows as the rate over the smaller class gets smaller. And what I claim is that whenever you plug the optimal rate for that I showed for alpha and beta known in here, we get a rate that's too large over this larger class indexed by alpha. Okay, this is going to become clear right now. So let me fix gamma equal 1 here, and alpha equals 0.5. Okay, so this is what the class of problems we construct looks like in the lower bound. So you can either be against the problem where there is no bump and just a bump here of smoothness 1. So if you're facing this problem, the true smoothness of your problem is 1. But if there is actually a hidden bump somewhere, then the true smoothness of your problem is 0.5. Okay? And if you want to find this maximum, then you necessarily have to pay some regret, because you need to sample here if there is no, if it's not indeed a bump. Okay? And what we show is that if you're willing to pay the optimal rate over the class with gamma equal 1, which is of order n to the 2/3, then necessarily over the other class indexed by alpha equals 0.5, you have to pay a regret that's larger than the optimal rate over this class. Okay? So two important takeaways from this proof. First, we see that the maximum is not, the value at the maximum is not fixed across the set of problems that we consider. And this is a very important point to create some kind of exploration-exploitation dilemma that's impossible to solve optimally and adaptively. And the second thing that I just mentioned is that the optimal rate is also not fixed across the set of problems that we consider. Okay, so this naturally led us to consider the problem of learning with extra information. And what we show is that if some extra information is given to the learner, for example, in the form of knowing the value that the function takes at the optimum, or the rate that we can hope to achieve, then there exist optimal adaptive procedures. So let me conclude with an open question that I think is interesting, which is whether there are other shape constraints that make sense in practice that also allow for adaptivity to the smoothness in this setting. And one, I think, promising direction is the question of unimodality or quasi-convexity. Thank you.
Questions, comments?
Please.
Can you perhaps say something about the variance that you're assuming? So you're saying that the expected value of f given x.
Yeah, so I'm assuming that the noisy rewards are bounded.
But they are independent of x, they are independent of f. The variance.
So they're given by a function of xt and they are IID.
No, the variance, the expectation of f of x, the variance of this random variable y. Does it depend on x? Does it depend on f?
We're just making a bounded assumption here.
Bounded assumption.
Yeah. So I know there are results, for example, if the true maximum gets close to 1, then you have a variance effect and other things can happen. But this is not the setting that we're considering.
Okay, thank the speaker again.